How does impedance matching prevent signal reflections? Imagine you're trying to push water through a pipe, but the pipe suddenly narrows or widens. Some water bounces back, causing splashes and turbulence. In electrical circuits, a similar thing happens with signals traveling along wires or transmission lines. When the impedance of the source, the line, and the load are not matched, part of the electrical energy gets reflected back toward the source. These reflections can cause problems like signal distortion, noise, and timing issues. Impedance is like the resistance to alternating current in a circuit. It combines resistance, inductance, and capacitance into one value. In AC circuit analysis and circuit theory, the characteristic impedance of a transmission line depends on its inductance and capacitance per unit length. This impedance stays the same along an ideal line. When the load impedance matches the characteristic impedance of the line, the energy from the source flows smoothly into the load without bouncing back. The key to understanding this is the reflection coefficient, which measures how much of the signal bounces back. It is calculated by subtracting the line impedance from the load impedance, then dividing by their sum. When the load impedance equals the line impedance, the reflection coefficient becomes 0. That means no signal is reflected, and all the energy reaches the load. Reflections are not just a minor annoyance. They can cause ringing, overshoot, undershoot, and jitter in signals. These effects are especially problematic in high-frequency and high-speed digital circuits, where timing and signal shape are critical. Reflections can also lead to electromagnetic interference, which disrupts nearby electronic devices. To prevent these issues, engineers use impedance matching techniques. They design transmission lines with controlled impedance by adjusting the width and spacing of printed circuit board traces. They also add termination resistors that match the line's impedance at the load end. For example, a 50-ohm transmission line should be terminated with a 50-ohm resistor. This ensures the signal is fully absorbed at the load, preventing reflections. In some cases, impedance transformers are used to match different impedance levels. These can be specialized components that change impedance values to match the source and load. Proper impedance matching keeps the signal clean and strong, allowing for reliable communication and power transfer. In summary, impedance matching prevents signal reflections by making sure the impedance of the source, transmission line, and load are all equal or very close. This eliminates the discontinuities that cause reflections, ensuring maximum power transfer and clear signals. It is a fundamental concept in electrical engineering that helps keep circuits working smoothly, especially at high frequencies and speeds.